Hello, we'll get started now. My name is Rogelio Sullivan. I'm with PowerAmerica, and I'd like to thank everyone online today for joining us for our final technical webinar of the year. We've had a pretty active season with webinars on the first Wednesday of each month and first or second Wednesday of each month. And we're really pleased to have Bob Kaplar from Sandia National Laboratories with us today. Today's webinar will be recorded and subsequently posted to PowerAmerica's YouTube page, so you'll be able to watch it again. If you'd like a copy of today's presentation, please email me. I'll send it out in the chat window in just a minute. I'll send my email address. And then finally, because of the large number of participants online, the way that we're going to handle Q&A is that send your questions through the chat window. I think you'll see an option for chat at the bottom of the screen, and you can start sending questions right away. And as soon as Bob is finished presenting, I'll read out the questions for him to respond. Today's webinar will be 45 minutes and then 10 to 15 minutes of Q&A. So we'll be getting lots and lots of good information from Bob Kaplar. So with that, I'll introduce Bob, and then he'll begin his talk. Bob Kaplar received a BS degree in physics from Case Western Reserve University in Ohio, and his MS and PhD degrees in electrical engineering from Ohio State University in Columbus. He joined Sandia National Laboratories in Albuquerque, New Mexico in 2002 as a postdoctoral researcher and was subsequently a member of the technical staff, and he's now manager of the Semiconductor Material and Device Sciences Department at Sandia. His research is focused on wide and ultra-wide bandgap 3-nitride materials and devices for power conversion applications. And with that, I'll turn it over to Bob.
Okay, thanks, Rogelio. And can you hear me okay still?
Yep, we hear you clearly.
Great. Okay, so thanks again for the introduction, and also for the opportunity to present this work at the webinar here. So this talk will be on the development of high voltage vertical GaN PN diodes. As noted in the footnote there, I'll talk about a few other device types at the end, but the majority of the talk here is focused on the PN diodes. This is done under an ARPA-E project under the Open program, and specifically the Open Plus kilovolt devices cohort that's managed by Isha Kizlyali. And so, of course, we'd like to acknowledge the support of ARPA-E. Also like to recognize the team I have listed here. And so we have quite a big team for this program, and everybody listed here is done what I would term the real work. I'm coordinating this program, but everybody here has made very significant contributions. So we've got our team at Sandia, great team at the Naval Research Lab in Washington, and that effort's being led by Travis Anderson, and then also Shrabanti Chowdhury's group at Stanford. And then Oscar Aktash at Edynix doing a lot of our reliability work, and Jim Cooper at Sunrisa, and of course Jim very knowledgeable about silicon carbide devices. So we're trying to make use of some of that knowledge for this program in the vertical GaN. So kind of with that introduction, I'll get into the presentation. So this is just a outline of what I'll talk about. First section, we'll discuss the motivation and just some general background on the vertical GaN. The project is kind of divided into sort of two parts. One of those parts has to do with producing these very high voltage GaN diodes focused on protection of the electric grid against electromagnetic pulses. And so I'll talk about some of the device work there, and these devices need to have very fast breakdown response time. So I'll talk about some of the testing we're doing related to that. And then the other portion of the project is really to try to establish a foundry process for these vertical GaN devices. And so some aspects of that include looking at wafer metrology. Of course, the processing edge terminations are a big topic, of course, and then just electrical testing, yield, and then we're also looking significantly at reliability and failure analysis. I'll talk about that towards the end of the talk. And then again, at the very end, just a few other, touch on just a few other projects looking at some other aspects of vertical GaN device development. Okay, so kind of moving into the motivation. So I'll spend a few minutes on this slide. I just want to give a little overview of what is the vertical GaN technology. So this is quite a bit different than the I think what most folks in the power field think of when they think of the GaN power devices, which is the HEMTs, typically grown on silicon substrates. And I know there was another PowerAmerica webinar, I think maybe about 6 months ago, on vertical GaN. So some of that was covered there. But these types of devices are quite different from the HEMTs. Their structure really more resembles what you'd see in like a silicon or silicon carbide discrete power device. And so I try to illustrate that in the upper left here, just a schematic of one of these devices. And this is not to scale, but you'd have a substrate here, and we're doing this on GaN, native GaN substrate. So it's a conducting substrate. The back contact is actually on the back of the wafer. And the key element here is this this drift region. So this is a low doped, thick epitaxial drift region. This is just like you'd see in silicon carbide device, for example, that holds off the voltage, but also imparts resistance. And then you have your anode contacts and your edge termination and so forth. So I just have an example. This is from a previous project, but this is an example that we did a few years ago. This was a vertical, GaN PN diode, and you can see pretty high breakdown voltage. This is close to 4 kilovolts. Pretty nice differential on resistance here. And this breakdown is in fact due to avalanche. I'll talk about that a little bit more later, but you often hear GaN does not avalanche. So that's generally true for the HEMTs, but for these vertical devices, the avalanche actually has been demonstrated by a number of groups over the years. Plot on the lower right just shows where that particular device lies. There's various versions of this plot out there, and actually quite a few more devices in the literature than I have shown here. But you can see where that falls, and I actually marked 3 different limit lines for GaN, and that's we're not really sure what the critical field is. That's something we're looking at in this program. I'll talk about that a little bit later in the talk as well. In terms of this particular ARPA-E program, the goals in the upper right of the slide here, we're trying to increase the breakdown voltage by a factor of about 4 from today's state of the art. The best I'm aware of that's been published is from a group at Jose University, about 5 kV. So we're trying to push that up all the way to 20 kV. Again, the thick drift region, the doping and so forth, edge terminations are challenging. And then we would like to establish that foundry capability, as I mentioned earlier. Okay, so I wanted to talk a little bit about these sort of 2 parts of the project. The first being this protection for the electric grid. And so one of the concerns for the grid is high altitude electromagnetic pulses. That plot on the left there just shows if you had a EMP event based, centered kind of around Omaha, sort of, middle of the U.S., just what the geographic extent of that would be. And so that, it's pretty big, right? And so this, these can affect the grid. It can affect a pretty large area. One of the issues is there's different components of those electromagnetic pulses at different time scales. So in particular, there's this fast component that's termed E1. It's typically less than a microsecond, but the rising edge of that is actually just a couple nanoseconds. And so that is presently unaddressed by the current technology, the state of the art being these lightning surge arresters. So the plot on the bottom right just kind of is, this is time scale, on more or less a log scale. And this part down here is less than a microsecond, currently not addressed. So one thing we're looking at is to develop these devices to address this need. And there's that reference there in case you're interested in more details on that. But more broadly, we're interested in medium voltage power electronics. So the MV in this case stands for medium voltage. And so this slide gets to that a little bit. And so I mentioned the critical field earlier. I think there's considerable debate in the community on exactly what that is for GaN still. And of course, it's a function of doping and temperature. And so people have tried to estimate it from devices, but recently there have been a few measurements of impact ionization coefficients. The one I've referenced there is from Trabante's group. And if you translate that to critical field under those conditions, you get about 2.8 megavolts per centimeter, which I think may be a bit higher than silicon carbide. But one other factor, of course, is the bulk drift mobility. And again, some debate about what this is, and I've had discussions with various folks on the team about this and tried to give some references there. But we're thinking for GaN, it's maybe somewhere around 1200 versus maybe 950 or so for silicon carbide. So that potentially does give some advantage for these medium voltage devices. Medium voltage, I'm defining somewhat loosely, more than 1.2 kV, kind of taking 10 kV maybe as an exemplar point for that. And so on the right, these are just some simulations that Trabante's group did, looking at efficiency of a power converter based on silicon carbide MOSFETs versus a CAVIT type of vertical GaN transistor. And so at the 1200 volt point, you can see some slight potential increase in efficiency for the GaN. As we go up to the 8 kV point here, we see about a 3% potential improvement. And so even though, of course, this is only 3%, but if you measure this from 100%, it's about a 25% increase. So, potentially there's some opportunities for improvement there. But these vertical GaN devices, of course, are pretty immature relative to silicon carbide and the lateral GaN as well. And so part of this program is to establish this foundry capability where we're looking at yield and reliability and these types of issues. Okay, so in terms of our team structure, as I mentioned, this is a pretty large team, geographically diverse, spread out across the country, and so coordinating this is one of the things we have to make sure we pay attention to. In terms of who is doing what, Sandia is doing all the epi growth for the program, as well as device and testing related things, sort of related to this EMP arrestor application. NRL, again, this is Travis' team. They're also working with the NIST NanoFab. They're focused on the foundry process. Also some FA and a few other things, primarily that foundry process. Stanford is looking at some aspects of the device design, particularly related to certain edge terminations and some topics and like the backside contacts, and also looking at some of this breakdown physics, ionization coefficients, so forth I mentioned. Over here, back on the left, these are subcontracts to Sandia, is why I have them over here. But the Dynix, this is Oscar. He's really more on the foundry side, looking at the reliability in the FA, and then Jim at Sunrisa again, helping with some of the device design. In terms of what are our targets for devices, so we actually have sets of metrics. This is showing breakdown voltage, but we have metrics for like on resistance, leakage current, various other performance parameters. But we kind of have it mapped out in terms of these breakdown voltage targets. So again, Sandia is doing the epi growth, And then these EMP diodes for grid protection, these are being fabbed at Sandia. So we have these 5, 10, and 20 kV targets. We're kind of in this 5 kV space right now at where we are in the program. And then NRL with NIST, with the foundry process, you know, these are kind of your standard voltage ratings, 1.2 and 3.3, and then up to 6.5 kV. And so we're, you know, again, we're sort of at a point in the program we're looking at the 1.2 right now. So I'll talk about that as we move forward. Okay, and then I think this is the last slide in the introductory section, and I'll talk about edge terminations more later, but it kind of permeates the whole program. So I wanted to just kind of discuss it here, you know, sort of globally. We're looking at different approaches for these high voltage EMP diodes. We're looking primarily at multi-step JTEs. So I've got a just schematic and then some simulation results there. Primarily a etch approach, but this could also potentially use an implant. For the foundry, in contrast, the primary approach is to use an implant, and we're looking at both guard rings and JTEs and combinations of those. And then as a mitigation to that, we're also looking at some potential bevel designs, and you know that might be useful for some of the higher voltage diodes in particular. Okay, so moving on to the next section, this is where I'll talk about some of the work on the higher voltage diodes for EMP protection, look at some of the device work, and then this fast breakdown response testing, which is, I think, pretty interesting topic. So this slide, this just shows an overview of what we're thinking about for these very high voltage diodes. So on the left is just the you know, schematic of the structure. This is the substrate. Again, you know, this is quite thick, not to scale. The key thing here is this kind of this lighter colored region here. This is the N-type drift region. And you can see this is pretty thick, 45 microns, you know, for GaN. That's pretty thick layer, and doping target mid 10 to the 15 per centimeter cubed. And so we have been able. This is Andy Allerman's work, the growth of these. We have been able to grow these and you know dope these. We do CV, and we see you know some variation across the wafer, but you know pretty close to this range. We've gotten actually down to kind of low 10 to the 15s. As far as I'm aware, you know, that's really state of the art for doping of these thick drift layers. And so then Mary Crawford's leading our fab efforts on this, and you can see, of course, the schematic of the structure, which I showed earlier. And then these are just a photo of some fab devices. These are smaller ones, but we've got some now in process up to a millimeter in diameter. So that's kind of what the devices look like. And then if we look at a representative IV curve, so just example shown here. One thing I do want to mention is actually the testing of these devices, both in forward and reverse bias, can be somewhat challenging, and there's I think an art to it in some ways. So like for example, this area I've circled, you know, there's some stuff down here which you know maybe we're not quite believing, and this has to do with just the SMU we used. We use you know typical equipment like Agilent or Keysight, I guess it is now, B1505. To get above 3 kV, you've got to use their 10 kV expander, which is not necessarily optimized for you know measuring like sub 1 kV and so forth. So the measurement can be tricky on these. So one has to be very careful about the interpretation sometimes. But in any case, with this higher voltage SMU, we see we do get a pretty nice IV curve and breakdown, you know, out above 4 kV. So pretty high breakdown. We estimate that's about 70% of the ideal planar diode value. Of course, that depends on the edge termination and so forth. We've got metrics on leakage current as well as just the breakdown, right? So you don't want a leaky diode. So that is 1 milliamp per square centimeter at 80% of the breakdown. So that'd be at 4 kV, targets 5. And you can see that there. The diodes do turn on as well. So also obviously very important. In this case, we get a specific on resistance. Of course, this is log scale. So kind of up here, a little under 3 milliohms centimeter squared. Okay, I do want to touch a bit on this avalanche breakdown and avalanche ruggedness topic, which I alluded to a bit earlier. So the stuff on this slide, this is actually from a previous program, but I thought it was a good way to illustrate this. Again, you often hear GaN does not avalanche, but it does. The material is capable of it. It just needs to be the right device structure. And so this is some examples of that. This is some temperature dependent breakdown on the left, and you can see as we increase the temperature, breakdown voltage increases. So that's characteristic of avalanche breakdown. If we plot that versus temperature, we get this T to the 3/2 dependence. So that's consistent with phonon scattering, limiting the breakdown. Again, consistent with avalanche. Moreover, the devices actually can show avalanche ruggedness. So this is an example of a study that Osgar did a few years ago, and you can see this particular device, it's simultaneously undergoing its high voltage and then high current at the same time. So you can calculate the energy in this pulse and how much energy that device sustained. And this study actually showed that devices could sustain multiple pulses like this before failing. So just wanted to emphasize the point about the avalanche. And we do need that for this EMP arrestor application. And so this is some work that Jack Flicker has been leading at Sandia here. We're trying to measure the time response of the avalanche breakdown. And so the way this works is the schematic of the setup shown at the top. We basically have our diode here at the edge of a transmission line. We hold it under reverse bias, and then we send a pulse down the transmission line, and then that puts the device into breakdown. And so since the device is going from a blocking state, essentially an open, to a short, it's still at high voltage, but it's now it's conducting. That changes the reflection coefficient at the end of the transmission line. And so by measuring the voltage as a function of time at various points in the system here, we can actually characterize that. So some of the raw data is shown on the bottom left here. So these are a couple different voltage traces, input and output, and the blue and the orange. And the one I want to focus on is it's this voltage probe shown here, this red trace. And you can kind of see this this transition here. And if we expand that out and fit an exponential curve, and so there's some little increase out here we're thinking about still, but fits decently, and we get a time constant about 1.3 nanosecond, which actually really is an upper bound because there's a time response in the system that's involved in this and so forth. But this is sufficiently fast to use as that EMP arrestor. So I think these are pretty neat measurements that Jack and some other folks here at Sandia have been able to do. So, okay. So that takes me to the kind of the second half of the project, which is the work on the GaN foundry process. So I'll talk about these various subtopics here. So as I mentioned earlier, Sandia is doing the growth for this. These are just some deliveries that Sandia has made to NRL as well as Stanford, and Brendan Gunning here at Sandia is leading this growth effort. And we've done some since I made this table as well. But you can kind of see, what we're looking at, different types of wafers, different drift region thicknesses, sort of the different experiments looking at the P layer, wafer to wafer variation, anode design, again, different types of wafers, drift region thickness, and the design variations, so forth. So we're growing these. These are for this 1200 volt process. The FE is nominally targeted at 1500 to give some margin. And so the wafers arrive at NRL. Again, Travis is leading the efforts with his team there at NRL, and undergo various metrology testing there. And so CV is one example of this. This is just one instance of that, and you can see the raw data at the top, and then carrier densities in the drift region extracted from those measurements, different points on the wafer. And so this is pretty good, pretty uniform across the wafer, matches pretty well with the design spec and then measurements that we do at Sandia as well. Another very important metrology that NRL has been doing is this optical profilometry. So this is essentially measuring the surface morphology of the wafers. And so you can see, again, an example with 3 wafers in the upper left. This is the raw data here. And what can be done is that raw data can be taken and, the wafer broken down into different areas that would, for example, correspond to if you had a device in that area. And then we can, based on the surface morphology, try to make some estimate of whether we think the device might fail due to excessive RMS roughness, for example. That's the yellow, or if there's a bump or a pit there, that's the orange color. Maybe it has both of those, that's the red, or maybe it's a good area in the green there. So this is just an example of breaking that into these different areas for these 3 wafers. We see, in this case, the drift region doesn't have too much impact on that. Kind of looking at the data in a little more detail, on the right hand of the slide, as you'll see in the upcoming slide, the foundry actually has a mask set that has these geometries A through F listed at the bottom there, with different areas, about 1/10 of a square millimeter up to 1. And so again, we can divide the wafer into these areas. And so those are the different panels, the sets of bars, or the 3 different wafers, and then the white, the gray, and the black here again are the different failure mechanisms. And so we can make some estimate of what we might expect to see, sort of based on area. And of course, larger area is tougher to get yield, right? And so that's shown on this slide. So we're not making devices this large, at least yet, but we can try to extrapolate, what we might expect based just on this analysis of the incoming wafers. And so this is an example with so-called LED grade wafer that contains these dot cores or bundles of dislocations on about a 1 millimeter square grid versus this laser diode grade, which does not have that. And so you can see, for different areas, 1 by 1, 2 by 2, 4 by 4, what we might expect. You see a little more green for this LD grade wafer. And so again, RMS roughness as well as particles can contribute to this type of analysis. Okay, moving on to actually fabricating some devices beyond that incoming wafer metrology. This is a mask set that the foundry is using, and so you can see those areas again designated A through F here. You might be able to see these little dot cores kind of in between there. Again, not on every wafer type, but on some. The device A might be considered a unit cell, again, about 1/10 of a square millimeter, and then the area is increased. It's increased just in the one direction, actually, to avoid these dot cores that are, again, present on some wafers. And there's some other features on here, kind of on the right of the layout, just, process monitors looking at contacts, the P conductivity, edge terminations, things of that nature. Okay, wanted to talk a little bit about the edge termination. Foundry's actually looking at a variety of edge terminations. Again, as I mentioned earlier, based on guard rings, also JTEs, combinations of the two. This example shown in the upper left is just a basic JTE. There is a isolation implant there as well. And so we're doing TCAD. The TCAD is this is actually kind of a mirror image. The contact is here on the left of the TCAD image. But we can evaluate things like the thickness of the implanted JTE region, doping profiles, and so forth. So we've been doing this for the various edge termination designs for the foundry devices. In terms of once we get the devices out, the testing that's shown here on this slide. And so here's a typical foundry wafer. You might be able to recognize that device pattern with the different areas there. And then here's a large area device under test. You do see some light emission that's, of course, it's visible, so sub band gap. And this plot in the upper left shows some representative forward IV curves for different sized devices. So this brown one here, that's the largest. So we do see higher current. Of course, we've gotten up to around 6 amps here for this device, so that meets our current density metric for the program. I do want to just kind of emphasize again here that some of this testing really, one has to be pretty careful about making sure this is done, correctly, and 2-point versus 4-point measurements, and there's various nuances in doing this the right way. So team has invested some time in really making sure this is done correctly. In terms of the reverse bias, here's an example of that, and so this is one particular edge termination design. This is guard rings plus a JTE in this case. And you can see these reverse bias curves, again, for different size devices, the A through F, and kind of two sets of those. And so we do see some devices kind of in this 800 to 1000 volt range, but fair number up here around 1300 volts. And so that's meeting our goal for this particular set. And I guess kind of what I'd like to emphasize here, the takeaway is the foundry effort is now producing multiple devices that are exceeding the 1.2 kV. That's about 90% of the parallel plane target, based on the EPI design. And so I think we're pretty encouraged by what we're seeing with some of these results. Okay, moving on to yield analysis. There's various ways one could define yield, based on breakdown or R-on or other things. What we're looking at here is actually on-off ratio of forward to reverse current. So we're trying to capture both the forward and the reverse modes of operation of the diode. And so what you can see, like for this wafer in the upper left, there's some variation. This was a wafer with a dot core substrate, and so like this one is aligned to the dot cores, whereas these other three are not. And you can see that doing that alignment results in the better yield, as you might expect. And so we're getting pretty good yield even on these large area devices. So this type of analysis is done on all the wafers passing through the foundry. Going back to the subject of edge termination, so I mentioned we had this mitigation to use a bevel design. So this is done at Stanford. Bevels are of course used in other material systems as well. So just a schematic of the idea, right? You've got this slope sidewall that's going through the junction here. So this is some work that Kay Zhang at Stanford's done, where he's done TCAD simulation of various bevel angles here. You can see the field distributions. There's kind of a hotspot there, so we record that. We're also interested in the magnitude of the field at the surface, like right at the junction, and then of course the breakdown voltage of the device. And we can put surface charge and other variations in here. He's generated this this plot on the lower left, and so plotting peak field. That's this hotspot in the blue, and then the avalanche voltage in the red. It's a function of the bevel angle. So kind of the takeaway here is that one needs a pretty small bevel angle with this approach, to get a good breakdown. And so some of these have actually been fabricated at Stanford. This is one example. They've done a couple different bevel angles. The example on the left there is actually a 1 degree. So that's, again, trying to get that shallow bevel for the higher breakdown. And so you can see the mask design here with multiple steps meant to approximate the bevel. And then these are some photos of fabricated devices. So this is before and then after a bake on the photoresist intended to smooth it out a little bit. And so you can see in these profiles, these are a little small, sorry, but this is about 1 degree here. And these have actually recently been tested electrically. And I don't have the data on here, but they're looking pretty good as well. So if we think this is useful, we'll probably this would be transferred to the foundry at NRL. Kind of last topic on the foundry work has to do with reliability and failure analysis. So this is being done by Oscar at Dynix, and so these are just examples of some of the equipment and a test board, and you can see devices on there. Much of this testing actually is done with individual power supplies addressed to each of those devices, so that helps with some of the cleanliness and fidelity of the data that we're taking. We have been looking at pre-existing diodes, but now we're starting to look at some of the ones produced in the foundry. We've got a couple examples of some of the tests that we've been doing. So one test is this high temperature reverse bias. This one, I believe, was at 150 degrees C, and so we're just taking populations of these GaN diodes and essentially just putting them at temperature and at some reverse bias and recording their behavior. For example, breakdown voltage shown on the left here, and you can see we're actually stepping up that reverse bias as a function of time, in addition to just holding the diodes during that time. So this is not much changing here. The leakage current, so it's similar type of test, and now we are seeing some variation across this population. So some just kind of stay stable, some show decrease. This one shows an increase, and then where these lines terminate, that's actually a device that's failing. So then the question is, why is that device failing? So we've done a fair amount of failure analysis work. This is one example where a diode that failed HTRB was had some emission microscopy testing done, and you can see at 1 kV low mag image this spot here, and then if we expand that and look at different voltages, you can see at 800 volts a little spot, and then increases as we go up. And so this is right at the edge termination, and so we think that failure is somehow related to that edge termination. And then kind of final thing here on the reliability work, this was high temperature operating life test. So now we're stressing the device under forward bias and then sampling IV curves periodically. And in this case, what one can see, so before on the left and this middle panel is after, this differential on resistance stays pretty constant, but then the IV curve itself actually kind of shifts outward. And so if you measure the current at a fixed voltage, that's manifested as a decrease in the current. That's shown here. And so again, looking at FA, we think this might be related to the P contact, some nonlinearity, perhaps some delamination or cracking occurring around that contact. So just another example of a reliability test. Okay, so that concludes really the main part of the talk on the ARP-E program. I did want to spend just kind of the last few minutes here talking about some other vertical GaN device development that we've been doing. So I've got just a couple slides on that. So this one, this is another ARP-E program. It's under the PN Diodes, and this is led by Andy Armstrong here at Sandia. And so this is looking at this issue of selective area doping in GaN. And so, there's a lot of devices like a JBS diode or a double well MOSFET that require these P-well type regions. And so this is pretty hard to form in GaN. The ion implantation can be pretty tough, although some groups like NRL has made really good progress on that. Our approach has been to do an etch and regrowth, where we actually would etch this out and then regrow the GaN and then get the device. But that can affect the quality of this interface. You can get leakage currents and reverse bias and so forth. So example of that is shown on the bottom left. This is a diode. It's not really a well. It's just like a planar structure, but continuously grown diode in black. And then if we do this ICP etch and regrow, then you see this curve with this increased leakage current. And so there's some damage at that junction. If subsequently an RIE, if it's an ICP plus an RIE, that leakage current actually recovers, in fact, a little bit lower than the continuous. And so that RIE step really cleans up that interface. And Andy's been able to correlate that with this DLoss spectra. So this is a technique where shine light on the device. That's this photon energy on the x-axis here, and then that empties out at deep levels, and so then you can characterize what deep levels are in the material. And so continuously grown, that's this black spectrum. So we see this thing step up just above 2.5 eV or so. The red one is the ICP, and so now this inset is a blow up of this region. You can see this new state starting to come in about 1.9 EV, and then if you do the RIE, that actually goes away. And so Andy was able to correlate this 1.9 EV defect with the device performance. So kind of nice, looking at some basic spectroscopy and correlating the performance, and then was able to fabricate this nice device with a JTE using that full process with low leakage. Couple other devices. So we've also been looking at JBS diodes. This is actually work funded by the Vehicle Technologies Office out of DOE. So looking at automotive applications. And so JBS, of course, has that selective area dope, type structure, as you can see in the schematic in the bottom. And so, we've used some of these these techniques I described in the previous slide here, and you can see this cross section, and gotten devices. Here's a representative one. This is actually the forward turn on, so this is not the breakdown here. This is forward turn on. Less than 1 volt. You can't see it on this plot, but it's sub 1 volt, and then you can see the leakage current. We get out to about 1500 volts or so. No edge termination on this particular device, so we're trying to add that. So that's just one example of a more advanced, or more complex device structure. And then the other one we've been working on are these vertical MOSFETs. And so looking at two types, one is a trench MOS, and then one is the double well MOSFET. They kind of each have their own challenges. The double well has this selective area doped region, so we thought the trench might be a bit easier to get started with, but of course it's got a etch surface to put an oxide on and so forth. So they each have their challenges. This is work led by Andrew Binder at Sandia here. And then I think this is last technical slide here. Just some examples of the devices we've made and data. So we've got a single finger and a 4-finger version of this, and you can see some representative data. So, it does work as a transistor. This particular one had ALD SiO2 gate. We've looked at aluminum oxide as well. But, pretty decent gate control and about 400 milliamps per millimeter. If we look at the transfer curve, threshold voltage about 8 volts, so nice positive threshold, and then on-off ratio close to 10 to the 8. So, that's pretty good too. And then the transconductance curve also shown. So, just wanted to show a couple examples of some other types of devices. So just in summary here, I covered the motivation, why we're interested in vertical GaN. I just kind of want to reemphasize that point that vertical GaN is pretty different than the lateral GaN HEMTs. And so just kind of want everybody to keep that in mind. I discussed the diodes we're developing for the EMP protection problem, and some of that fast breakdown testing and so forth, and then of course the foundry process with the various aspects to it that we went through, and then the just a couple quick examples of some other devices. And so I think that that concludes presentation, and so hopefully everybody's still there, and I could take some questions.
Thanks, Bob. That was an excellent presentation. Really great information about some of the advanced research you're doing there at Sandia on vertical GaN, and also including a lot of collaborators that PowerAmerica's worked with. So it's good to see you working with Shrabanti Chowdhury, for example. Yep. We do have a few questions already, so I'll read them out again, and you will answer them, and we'll just go through till we get through them all.
Okay.
We have a little time. So what epitaxial tricks can you use to tune the ND value and reduce it further? This is a multi-question question.
Okay, yeah. So again, getting that doping down is one of the challenges. So one of the issues is tend to get compensating defects, for example, due to carbon, like in the epi layers, and so you're balancing your intentional dopants with some of those unintentional that would be like a p-type state in this case. And so it's actually a difference of two things. So trying to balance that is somewhat tricky. I would say that's probably the main thing. I mean, there's and the growers, they could give more details on this, but variables such as growth rate, temperature, things like that, one has to tune to get these things in balance.
Okay, what is your take on MBE versus MOCVD grown samples for ND and device performance metrics? And what is the substrate who's the substrate manufacturer?
Yeah, so MBE, we're looking exclusively at the MOCVD. I think for these types of devices, where you need these drift regions that are tens to maybe, over 100 microns thick, the growth rates for MBE are probably just going to be too low, to get there in a practical sense. There are various substrate manufacturers out there. We've done a lot of work on the Mitsubishi, but there's a number coming out of Japan, and some of the best ones are the mono substrates, which are out of Poland. There've been some issues with availability of those and the size and so forth. I think they're kind of back up and running now. But the substrates, these are all 2-inch substrates. I've seen some people claim to have larger ones. I guess I haven't actually ever seen one physically myself. I've seen some photos of them, but the substrates are kind of one of the challenges, I would say, both in terms of reproducibility and just variations manufacturer to manufacturer and so forth.
And the last part of that question, do you do any substrate preparation before growth, either in situ or ex situ?
I'm not sure all the details on that. I'd probably have to defer to one of the growers on that. So yeah, I might have to get back to you on that one.
What is your take on the use what is your take on the use of an emerging N-polar GaN architecture for your device concepts? I assume thermal management is not going to be very helpful for reliability, as it is the case in GaN HEMTs. Is that true?
So okay, yeah. So this is talking about the nitrogen polar versus the metal polar phase. So we haven't really looked at that. Although in this case, these devices do not rely on the like the polarization induced doping like that you would have in a hemp, for example. So where that polarization discontinuity essentially induces the channel, right? And then if you're reversing that, that kind of really changes your device structure. Here, this is just impurity doping. It's essentially it's a homojunction. There is top and bottom surfaces that potentially could affect the contacts, surface passivation, and so forth. But I wouldn't think it would impact the kind of the actual junction too much. Would be my first thought on it.
Okay, next question. What is the typical size of widely available bulk GaN substrates? Also, what are the future prospects of bulk GaN in your opinion?
Yeah, so again, we've looked primarily at the 2-inch wafers. You can get smaller pieces, square centimeter, 1 inch. I have seen some, kind of marketing type stuff from some companies saying they're up to 4-inch. I haven't actually ever seen one myself, but I think it is improving. Honestly, I think some more investment in that, in the U.S. probably would be a good thing. A lot of it's coming from Japan, and I mean, they are getting better and so forth. But still expensive, and I think the market maybe has to kind of take off a bit, to really open the floodgates on that. Would be my thought on it.
Okay, a compliment to you saying excellent talk.
Oh,
And
thank you.
then
Appreciate it.
what are the MOCVD growth rates for the lightly doped GaN drift regions?
So those could typically be a few microns an hour. These can be pretty long runs, and so it might be an overnight run. In some cases, you may actually have to worry about things like one of your sources might start to get depleted, because these are such intense growth runs. So yeah, so getting that thick, it's it's challenging, and again, Andy's been able to do that really well.
Okay, another compliment from a questioner on the excellent talk.
Okay, thank you again.
And he also asked, can you give us an estimate of the order of critical electric fields measured in GaN vertical bipolar structures?
Right. So I kind of alluded to this a little bit. It does vary. The reports, we've actually done some studies where we plot kind of reported values of critical field, as a function of year that the value was reported. Some of the highest estimates have been up to 5. I think that's probably too high. One of the issues is the values, a lot of the values reported have been derived from device measurements. And so that's really tough because, you've got things like edge termination, interfering. It may not be the definition of the critical field, which is just the ideal infinite planar case. People tend to not normalize to a constant doping and so forth. Probably, I can maybe go back. This one I mentioned, there was a few studies. So I mentioned this one reference here. This is from Shabranti's group. There's a couple other recent studies. I think one was maybe from Notre Dame and one was from Japan, but they actually measured the ionization coefficient. So I think the way to really do this is to get good measurements of these ionization coefficients, and then you can translate that into a critical field at a certain doping and temperature. And so that's where this 2.8 value came from. So this is the best I'm aware of right now, but this I expect this will probably keep evolving, particularly as material quality continues to improve and stuff like that.
Okay, thank you. Next question. Can you comment on the application space of vertical GaN PN diodes, and then in parentheses with higher turn-on voltage of silicon carbide JBS diodes?
Yeah, so I think the vertical GaN really is more suited for some of these higher voltage type applications. Maybe similar spaces as some of the silicon carbide. In terms of like a PN junction versus like a JBS, say, of course, you don't want to have that 3 or 3.5 volt turn on associated with the PN junction, right? And so because that's a significant loss mechanism. So that's why us and other folks are trying to think about JBS diodes and so forth. The PN diodes, I think, do have some niche applications like the EMP arrestor. It is a simpler structure, at this stage of development. The junction tends to be more robust and so forth. Here, we're really, with the foundry, for example, trying to use it as an exemplar to, illustrate the merits of the technology and, develop the various process modules. And presumably in the future, that could be extended to more complex devices, such as the ones I touched on at the end of the talk.
Thank you. Can you comment about GaN substrate size and cost?
Yeah, so I've discussed some of the size stuff earlier. The cost, it does vary some. Typically, it's a few $1,000s for like a 2-inch substrate. The prices are going down somewhat. I know like Mitsubishi just they kind of shifted their offerings and sort of what was the high end previously is maybe kind of more now the standard. But so they are expensive. But I think this is coming down.
Okay. For 4.5 kV PN diodes, what is the largest device area you can achieve with current foundry, and what is the major challenge to scale up the device size and current rating?
Yeah, so the largest ones we've been doing are these kind of 1 millimeter squared. I know there are some previous efforts by some other groups that have done like I think up to 4 by 4. Those were at a lower voltage rating. I think a lot of the challenges have to do with the really the quality of the starting wafers, being able to grow the epi over a long period of time without having particles and things like that. There can be challenges there. So a lot of it has to do with the underlying materials.
Thanks. What are the technical challenges in developing GaN JBS diodes with higher voltage, say greater than 10 kV? And do you think that GaN JBS diodes have potential to become superior to SiC JBS diodes at 10 kV or higher voltage?
Right. So I would say the main challenge really is, I guess I could go back to that one slide. Yeah, this, so the quality of this regrown interface. This PN junction is going to support that high voltage. So this has got to be not just high breakdown, but low leakage. I think assuming this type of stuff is worked out, then yeah, potentially given a bit better critical field and mobility, at some point probably you could get past what silicon carbide's doing. But of course, silicon carbide has a pretty big head start, right? And so there's some development to be done to get to that point.
Thanks. Should one expect significant differences in reverse recovery behavior of GaN pin diodes compared to silicon or SiC pin diodes?
Right. Yeah. So maybe I'll go back to this slide on this one. So this particular set of stuff I showed here, this is for time dependence of reverse breakdown, but this system was actually modified from one where we measured reverse recovery. So we went from a forward to a reverse state rather than from a reverse blocking to reverse conducting. We were getting values less than 2 nanoseconds for that reverse recovery, and that was in a PN junction, and so that was kind of indicating, again, there was a system response time, so that's sort of the upper bound on that. So there's essentially no reverse recovery time, even in a bipolar device. In a Schottky or JBS device, of course, there are no minority carriers, so you wouldn't expect anything. So, so I think these can potentially be very, very fast. I know silicon carbide Schottkys are pretty fast, but these GaN diodes, even if it's a PN, could have extremely short reverse recovery.
Thank you. Next question. Should one expect significant differences in reverse recovery? Oh, no, I think I asked that one already.
Yeah, okay.
All right. This device structure seems very different from the hemped structure we see a lot in the literature. Do you see any challenges with P-type doping, and how fast is this device compared to hemped structures?
Yeah, so so the device, it is totally different from a hemp, and so I want to kind of re-emphasize that. I mean, the device structure, actually maybe this one is a better example in the upper left. This is the structure itself is quite similar, to what you'd see like in a silicon carbide diode. The P doping can be a little tough. The magnesium dopant and gallium nitride's a deep dopant, and so there can be some challenges with this. And we are doing experiments looking at these anode designs and so forth. You don't want to make it too thick. You want to make sure you got enough holes though to inject across the junction and so forth. And then the ohmic contact can be a little challenging. I guess I'll mention we do a lot of work on AlGaN also, so that the band gap gets wider, and then the P-type that gets even tougher. But I think in the GaN it's challenging, but there's a pretty good handle on it, and the devices clearly work and so forth.
And finally, I assume thermal management is not going to be very helpful for reliability as it is the case in GaN HEMTs. Is that true?
So in terms of thermal, so you've got the thermal conductivity of GaN, so that sort of is what it is. You don't have a lot of the interfaces in these types of structures like you would in a HEMT. So like a HEMT, it's grown on silicon. It's got the strain management layers and so forth. It's a pretty surface sensitive device. This really is kind of more a homojunction device. So the types of things you need to think about for thermal management are more similar, I would say, to what you'd have like in a silicon carbide vertical diode. Of course, it's a different material and slightly different thermal conductivity, and there's variation between P and N type and so forth. But it's not as interface intensive a device as a HEMT. So you don't have those you won't have those bottlenecks, I would say, at those interfaces.
And one last question. In your knowledge, have these GaN diodes even been tested under conditions of switching operation in a power electronic converter, say a simple buck converter?
They have. And so let's see, I think I had one example that was this plot on the right. So, in this case, these diodes were run in this converter to test the avalanche ruggedness. We've run them in different converters here at Sandia. So yeah, so the answer to that, short answer is yes, they have been.
Okay, wonderful. All right, thanks again, Bob. That's the last question. Thanks for sticking around for the long Q&A session. That's just evidence of the great interest in this topic and the excellent presentation that you prepared. So again, thanks very much for taking us out on a high note for the last technical webinar of 2020.
Okay, yeah, no, my pleasure. And again, thank you for the opportunity, and thanks to everybody that attended. I appreciate it very much.
And just to confirm, the PDF that you sent to me is okay for sharing with the people who requested copy of the presentation.
Let me double check a couple things with the team, but I think at least most of it should be okay.
Okay, great. All right, thanks again, Bob. Have a wonderful day, and thank you all for joining us this afternoon.
Okay, great. Thanks.
Bye.
Okay, bye.